Hey everybody, welcome to today's lesson. Today we're going to be talking a little bit about Charles' Law. Again, we've already learned Charles' Law. This is just really so that you can have this in your notes. And then I'm going to introduce another gas law to you, which is called Gay-Lussac's gas law. And then we have just a couple more to go after we can get through these two. So let's go ahead and dig in. So first and foremost, we do need to talk a little bit about temperature. Again, this was mentioned in class, but when we are working with gas laws, we cannot work with solely degrees Celsius. We run into an issue where we end up getting these negative numbers because it can very easily reach negative degrees Celsius, as well as undefined values when we are working with a zero in the denominator. So we really work with two different types of temperature in this course. Again, Fahrenheit, that's cool. The US uses it, but it's not really used for science courses. So we're going to use degrees Celsius. Okay, or we're going to use Kelvin. Again, it's not degrees Kelvin, it's just Kelvin. And to convert between those two, we are going to do Kelvin equals degrees Celsius plus 273. And again, this equation is on your reference table. So this is not something you need to memorize. You can find it on the reference table on the back side with all of our equations. I know that some people also who love being precise, you can also do Kelvin equals degrees Celsius plus 273.15. But again, that's really over the top for this course. For Regents level chemistry, you can stick with plus 273 to keep it easy. Now, we again already talked about Charles' Law, but it asks us to make a general statement about the relationship between temperature and volume, assuming pressure is held constant. So if we're comparing these two values, as temperature increases, okay, the volume also increases. This is a direct relationship. Okay, similarly, if we said, if we were to say if temperature decreases, volume would also decrease. Okay, and again, you can really envision this if you're thinking about a balloon that can expand and contract. If you think about how we've defined temperature, again, remember that means average kinetic energy, how fast our particles are moving. So if in my balloon, right, my particle temperature increases, okay, if we increase the temperature, we actually end up with particles that are moving faster. And I didn't really do a good job of drawing the balloon bigger. Maybe you can do that on your own. But our particles collide more frequently with our balloon, okay, and with greater force, and therefore that causes the balloon to expand. Okay, if we decrease temperature, okay, what's going to end up happening is those particles inside are going to collide less frequently with less force, and it causes our balloon to shrink. And again, I'm not an artist, okay? But you have to really think about it in terms of what's going on with those molecules. All right, so what would this look like graphically then? Again, with Boyle's law, we looked at an indirect exponential relationship. When we're working with Charles' law, with volume and temperature, it's direct, okay, and it's linear. So we actually end up with just like a nice straight volume versus temperature linear relationship for our graph. Now, our mathematical equation that we're going to use for Charles' law, okay, finally, yes, you can set it up almost using a proportion, but it's going to be V1 over T1 equals V2 over T2. And again, I'm going to star this and say, don't forget to convert to Kelvin. Okay, it's very important with gas laws to convert to that Kelvin temperature. So let's go ahead and do one example for our notes. So we have here, okay, volume versus temperature, initial conditions versus final conditions. Obviously, we are looking for our final temperature here. It becomes our unknown. Before I even start plugging things into my equation, though, I noticed that in my table, my temperature is still listed in terms of degrees Celsius. So I do need to go ahead and convert that. So we're going to do 273 minus 50. That's going to give us the 223 Kelvin. But again, let's plug it into the equation. So Kelvin is equal to negative 50 degrees Celsius plus 273, and that's going to give us 223 Kelvin. So we have V1 over T1 equals V2 over T2. Okay, let's plug it all in. So we end up with, I'm sorry, I read this entirely wrong here. We do actually also have to convert this initial temperature. For some reason, I was reading it differently. So our final volume is unknown. So let's go ahead and solve this. So 100 plus 273 gives us 373K. Okay. Whew. So here we go. So we have volume is 1 liter over our initial temperature, 373 Kelvin. And that's going to be equal to unknown X over 223 Kelvin. And again, you should always check yourself before you solve a problem. We know that our temperature is decreasing. That means our volume should also decrease. This way, if for some reason you end up getting a larger volume, that you know you've done something wrong. Okay, so why don't you go ahead, take a moment, pause the video, solve this problem. What answer do you get as your final volume of this balloon, or of this, I don't know, whatever we're looking at, gas. Okay, and if we do solve this through, we end up getting 0.598 liters. That I would probably round that to about 0.60 liters. Okay, so there we go. We have our volume. It's lower than our initial volume. That's what we'd expect to see. Okay, and that is Charles' law. Again, the relationship between volume and temperature if pressure is held constant. So now let's go ahead and take a look at Gay-Lussac's law. This is actually not a law that's taught on the Regents. You don't really need it for the Regents, but we've already talked about all of the other conditions and how they're impacted. So I figured, why not introduce Gay-Lussac's law, which is going to be the relationship where the volume is held constant. What does it look like for pressure versus temperature? So what I wanted to kind of think about, or look in these boxes up top here, is I wanted us to go ahead and just think about, in terms of container, what this looks like. So if I have, okay, a container here, the volume is constant. So this is a rigid container, which means that the shape cannot change. My volume cannot change. Okay, so I have a rigid container here. Okay, and let's say I'm starting at, I don't know, okay, 100 Kelvin. Okay, think about what that means for the pressure that's being applied versus, again, rigid container, size cannot change, though I did just probably not draw that to scale. Okay, and we increase the temperature to, let's say, 300 Kelvin. Okay, what's going to happen to the speed of my particles inside? Okay, my speed of my particles, increased temperature means increased average kinetic energy, which means my particles are moving faster. So if they're moving faster, what's happening to the force with which they're hitting the container? Okay, the force with which they're hitting the container is also increasing. So what's going to happen then, do you think, to that pressure? Is there more pressure or is there less pressure? Okay. And so let's go ahead and make a general statement here about that relationship. Okay, so as temperature increases, okay, our pressure is going to also increase. Okay, this is again a direct relationship. Okay, again, and this is true if volume is held constant. So we end up with this increased temperature, increased movement, increased force, and therefore increased pressure. Okay, direct relationship. And again, if volume is held constant. So it is also, again, important to note that we do need an equation for this. It is a direct relationship. So similar to Charles' law, we're going to go ahead and set this up in a division problem, in like a proportion style division. I like to remember the difference between Boyle's versus Charles versus Gay-Lussac's, indirect versus direct. Direct is division, indirect is multiplication. That doesn't really help, but division is direct relationships. So let's go ahead and create that equation. So our equation here is going to be P1 over T1 equals P2 over T2. Again, note that you need to convert to Kelvin anytime that we are using this temperature in the denominator. Okay, so we have our final conditions and our initial conditions. So let's go ahead and set this up. So we end up with P1 over T1 equals P2 over T2. Okay, our initial pressure is 1.8 atmospheres over our initial temperature, 150 Kelvin. It's so nice, it's already in Kelvin for us. Okay, X atmospheres over 750 Kelvin. Now note that our temperature again is increasing significantly here, so you should expect to see that our pressure will also increase significantly. Okay, so why don't you go ahead and take a second, pause the video and solve. Okay, so we end up getting 1.8 divided by 150 multiplied by 750, which is going to give you X equals 9 atmospheres. Okay, so we have a significantly larger pressure. So how would we represent this graphically? Again, it's a direct relationship. So P versus T, and we end up with a nice linear relationship. Okay, that's Gay-Lussac's law, pressure versus temperature if volume is held constant. I wanted to end today with just a fun video that I love showing when I'm in school. Unfortunately, we don't have liquid nitrogen in school, but I just think that this video is so excellent. It's an MIT physics demo, balloons and liquid nitrogen. So let's go ahead and take a look. In case you can't tell what the balloon animals are, a giraffe, a wiener dog, a poodle, and a swan. And if you're unfamiliar with liquid nitrogen, it is super, super cold. So in this experiment, pressure is held constant, right? The atmospheric pressure isn't changing. But we did adjust the temperature, and as a result, we're now seeing a change in temperature. Okay, cool. So I love that video. Thank you guys for watching that with me. Again, if you have a balloon at home, you can try to fill it up and put it in your freezer and see what happens. I would recommend filling it.
This is a beaker full of a little bit of liquid nitrogen.
I would recommend not filling it entirely, only just a little bit, and then letting it come back to room temperature. All right, everybody, thank you so much for watching, and have a great rest of your day, and I'll see you tomorrow.